Just random variables are not going to be negative. If you think about that, there's never going to be a negative height of somebody. There's not going to be a negative time that somebody is trying to get somewhere. There's not going to be a negative amount of things. So since our continuous random variables are never going to be negative, we know that the function has to be greater than or equal to 0, always. And since when we take this integral going from the negative infinity to infinity on both directions, it sets a probability, and we know that it's going to go from 0 to 1. The entire integral over real squared is going to be equal to 1. So this is basically saying as x goes from negative infinity to infinity, and as y goes from negative infinity to infinity, then the function, the integral of the function, dy dx, will equal 1. And now we can use these to verify that certain functions are joint density functions. So say we have a generic function x and y equals to sum g of x and y such that x is between a and b, y is between c and d, and it's 0 everywhere else, then we can take the integral of this from over all directions and see if that comes out to equal 1. So if we're looking at this this graph right here, we are going to get something like the cake piece that I was talking about, because we have where under a small section we've got this curve, but then everywhere else we've got 0. So we know that everything about the density function is wrapped up between all of this. So now we can see that integral from a to b and c to d of that function dy dx. If this equals 1, and you can't forget about it being positive, and it's greater than or equal to 0 for all of the domain. If both of these are true, then it is a joint density function. And we can use these joint density functions just the way we did use the probability density functions in section 6.8. Because if you wanted to find out for this generic thing, P for probability for x is less than or equal to 2, and y is less than or equal to 3. So that's basically saying if we have like a short distance to travel, what's the probability that we're going to make it there, and then we're going to make it to that next distance. So if you have distance x being the first distance for traveling, and distance y being the second distance, and they're not dependent on each other, then we can see like what's probability that we're going to make it through distance 1 in 2 minutes, and then through distance 2 in 3 minutes. So basically you just use this as you did with one variable to change your bounds. So I guess this would be, if we just had this function, we could go from 2 to b, and then 3 to b, and it would end up giving us the percent probability that we would